All right, good morning, everybody. Welcome to Lecture 5, DSCI 512. So in the last week, we've covered recursive functions and data structures. And when talking about recursive functions, I told you that these recursive algorithms are most appropriate for a particular type of data structure that's called a recursive data structure. And a recursive data structure is a type of way of organizing data that is defined in terms of itself. And we've talked about trees, for example, binary search trees, and also things like KD trees. And we discussed how each node of the tree can be taken as it's a tree by itself, and so on and so forth. This is the notion of a recursive data structure. So we have already been talking about the idea of storing data inside of nodes and then having some relationship or connection between the nodes. In this lecture and the next lecture this week, we will be talking about graphs, which is a generalization of the idea where we can store entities called nodes, and also we can also represent the connection between those entities using edges. So the trees that we have discussed last week are a special case of a more general concept called a graph. Okay, so let's get started. So I'm going to run this code, and this is just a bunch of just some options given to the plotting packages. Okay, so a graph, again, is a set of entities and then connections between those entities. And examples could be, we have a lot of real-world examples for graphs, where a graph could be an ideal data structure for storing information about those real-world situations. For example, friendships on Facebook. So there are a lot of people on Facebook, and some of those people are connected by friendship connections. So I'm friend with this particular person, the other particular person, but not with everybody. And these kinds of relationships are best represented using a graph. Each node can be a person. Each connection can represent friendship. Same goes for Twitter or other social media. We can also, for example, think of internet as a huge graph where the nodes are the computers on that network, devices on that network, and the connections are basically the network connections between those nodes. And you can immediately see how important it is to be able to represent it as such a data structure that exactly conceptually maps to what we have in mind. So a graph, and the internet itself almost completely maps itself to the abstract data type graph. And another example could be representing airports as nodes on a graph, and then representing direct flight connections between those airports using edges. Okay, so as you can see, a lot of real-world situations can be most efficiently and most conceptually accurately represented by graphs. Okay, so in this lecture, I'm going to be talking about a little introduction about graphs and the terminology that we use to define and describe graphs. And then we're going to look at different graph types. And then the bulk of this session will be on an algorithm called a graph search. And we will look at two different algorithms to do that, which is the most important part of this lecture. I'm going to be taking a very step-by-step approach. I'm going to use visualizations in order to guide you along the way. And then we're probably going to be looking at a few activity questions. Okay. All right. So a graph consists of a set of vertices or nodes. So this is the terminology could differ between different different textbooks and resources. So we can call the nodes either just nodes or vertices. And also the connections between those nodes could be called edges as well as links. Okay. So in order to work with graphs oh, that's cute. Okay. In order to work with graph data structures in Python, we can either go ahead and define our own classes. Using the concept of classes, we can define our own graphs. So define a node and define edges and like an init function and then an add function, a remove function, a count function, stuff like that. We can do that, but that would be tedious for our purposes, and we're not really that interested in that part of our coverage of graphs. So we're going to use a package called NetworkX, as you can see over here, which is a very powerful package in Python and very well maintained to work with graphs. So we're going to use that. I'm importing that here as NX, and I'm just going to show you the interface of this package, how we define graph objects and adding nodes and edges to that. So here, nx.graph, just something similar to pd.dataframe, defines a graph for us and stores this object inside of G. And then I'm going to use these methods in order to add nodes as well as add edges. So let's run that. Okay, A, B, C, D, E, these are the nodes. And for edges, I'm just going to say, okay, A and B, those are connected. B and C are connected, and E and A are connected. Okay. And then it has, this NetworkX has also a nice function called draw, which can quickly give us a visualization of what our graph looks like. And let's see. Yeah, this is our graph, and this is based on the connections that we have defined. And this draw params is something that I have defined all the way at the top here. It's just for visually presenting the results in a more legible way on the projector and on the notebook. Okay, let's go back here. All right, so every time that you run this, because of the algorithms inside of this package that take care of the visualization, you're going to see a different representation of the graph, meaning that the nodes are going to be moved around, but the graph is essentially the same. Okay? So again, run that again. Okay, each time it gets something slightly different. But if you want, we can also set the position of the nodes, and we can do that by using this position argument. And here, this is a function that gives a particular layout to the nodes, and spring_layout means that the links between those edges are represented using like springs, physical springs, and this helps to not to avoid overlapping between nodes and edges. So this kind of gives a nice visualization, and this is only for visualization purposes. It's not computational at all. Okay, so now if I do that and set the seed, okay, and now let's run it a couple of times to be sure that each time it gives us the same graph. Okay. And, all right, now let's talk about some terminology. So, the number of edges connected to each vertex is called the degree of that vertex. For example, here the node B, the degree is 3 because there are 3 incident edges on that node. And for example, the degree for the node C is 4 because there are 4 incident edges on that node. A complete graph is a graph where every vertex or every node is connected to every other node in that graph. That's called a complete graph. Okay, is this graph complete? No, it's not. For example, we can see that B and E are not directly connected. So we have at least one edge missing in order to make it a complete graph. All right, so in order to make it complete, I'm going to have to add these 2 other edges, and now when I plot that, this is now a complete graph. Every node is connected to every other node. Okay. Now, this NetworkX package has helper functions for us to draw complete graphs, and this is called complete_graph. It just generates a complete graph of with a certain number of nodes. Here we use 4, but we can do this for, let's say, for 10, and then this is a complete graph. Each node is connected to all other nodes. And we have 10 nodes. What will be the degree of each node? 9, exactly, because each node is connected to all other 9 nodes in that graph. Okay, and there are a huge number of these helper functions inside of network X to basically generate graphs of different types with different properties for you without having to manually go and enter all of those edges and nodes. Right. So more terminology. A graph is said to be connected if there exists a path between any pair of nodes. For example, if you look at this graph, which is a disconnected one, you can see that these bunch of nodes are separated from these bunch of nodes. There is no direct link between any of the nodes here and the nodes over here. So there is no way that we can go from A or C or B to E or F. Suppose that if these nodes represent airports, then it means that if we are able to do a kind of search over this graph, we would find out that there is no direct flight, for example, between A to F or A to E. So those two regions of airports are not connected. Okay, any questions so far? Yes. Yeah, it's defined by several edges. Yeah. It could be just one edge, but more generally it's defined by several edges. Okay, now a little bit more terminology before we get to the more interesting stuff. What we have seen so far is called an undirected graph because there is no sense of direction between those nodes that we have. D to C or C to D are basically taken to be equivalent. However, we can have directed graphs as well, and Network X supports both undirected and directed graphs. An example for directed graphs could be a social media like Twitter. So the fact that I follow a person on Twitter doesn't mean that that person also follows me. So that can be represented using a directed graph. Okay. All right, and the way that we can define a directed graph in Network X is by using this digraph function, this digraph object. If we, oh, sorry. Well, we went into debug mode too early. Okay, let's run this and then do that. Okay, now this is a directed graph. So we can always go from B to C, but we cannot go from A to C. Can we go from B to A? No, we can't because it's directional. There's no path from C to A, but there is a path from A to C. Okay. Now note that with the undirected graph, there was no difference between adding B and C, B first and then C, or C first and then B. But in this case, when it's a digraph, it's the directed graph, there is a difference between those. Okay, now this is a different graph. B to C and C to A. There is a path from B to A, but not from A to B. An example of directed graphs, here are MDS courses and the prerequisites for each course that is represented by this directed graph. So, sadly for me, DSCI 512 is not prerequisite for anything. So okay. Okay, so this graph that we can see here is not a tree. Why is it not a tree? So there's one reason over there, because in a tree we saw that each node only had one parent, but several children. But in this one, you can see that some of these courses have several prerequisites, and so they have several parents. And this is not something consistent with the idea of the tree. So a tree is something that just branches out. Never two branches never coincide and make a new branch. Okay, the other thing is that in a tree we have a kind of a root node at the top, and then everything is connected to everything through that root node. But for a graph, that's not necessarily true. Not every node should be connected to every other node. Okay, now, just like we had graphs like the ones that we looked at here, which each edge has only one direction, edges could have two directions. So in this case, there's a path from A to C and also a path from C to A. So this is bidirectional, but this one is just unidirectional. Okay, and this can be defined by using this syntax: add edge from C to A and also from A to C. Okay. Now, these directed edges can also represent loops over one single node. So you can have an edge that starts from A and goes to A. This network X supports that, but it doesn't visually show that in a clear, nice way. You will encounter examples of a self loop in DSCI 575 when you're working on Markov chains. Okay, so what we have looked at so far is these are called unweighted graph because those connections are just connections. They don't carry any weight, nothing else. Those edges do not represent any other information. However, we can also have weighted graphs, meaning that in addition to the edge itself, we can also have a weight associated with that edge. For example, here, this edge between A and B has this weight 2. For example, this weight could represent distances between two airports, or the cost of flights between those two airports. So this provides a way to find kind of, for example, if the nodes are different locations on the map, this could help us find the shortest distance between those different places. And this is essentially what something like Google Map does in a much more sophisticated way, obviously. Okay. Okay, and again, these can be unidirectional, bidirectional, and yeah. All right, we talked about this. All right, so this is it for the terminology and definitions. Now we get to graph searches, and the place where we discuss two different types of algorithms to do a complete search through the graph. So before moving on, any questions? All right, so when we have a graph like this, ENF on one side, DCAB on the other side, the question is, are these two graphs connected? So when we look at this, obviously we look from the top, we see with our own eyes that these two are disconnected, but within the system's memory, or the way that these data structures are represented, it's not that easy to say whether these are connected or not. It's like walking through a maze. Without looking from the top, you can't really say which path leads you to the exit, right? Because you are inside the maze. You have to basically go and look and search through the whole maze in order to find your way out. Okay, so it's the same case here with graphs represented inside of the computer. So we have to have an algorithm in order to be able to find whether this graph in its entirety is connected or not. Okay, so this graph, the graph is also by itself can be thought of as a recursive data structure, because if you take node 1 and just ignore that, the rest of the graph is still a graph. And if you, for example, remove this part of the graph and only look at this part is also still a graph. If you remove node F and look at E by itself is also still a graph. So it's a recursive data structure which naturally leads us to a recursive algorithm in order to search through the graph. Let's see how this works. So first of all, I'm going to show you the code, and then I'm going to show you visualizations of all the steps that are involved in looking through the graph to find whether the graph is connected or not. But before that, just to simply describe the idea for you, we start from a node, in this case, for example, node D, and then we want to see if D is connected to E, for example. Okay, so the way that we do this is that, okay, I have D, I'm going to look at its neighbor. The neighbor is C. Is C connected to E? Okay, in order to find out whether C is connected to E, I'm going to have to look at C's neighbors. Okay, I'm going to pick A. Is A connected to E? Okay, if that's true, then we just return true. If not, is B connected to E? Okay, and then we go in that manner. So we start from D. Is D connected to E? Are these neighbors connected to E? Are neighbors of neighbors connected to E? So when each one of those calls returns a true, we know that there is a connection between A and E. Yes? Oh, yeah, so this is one thing. So the question is, whether we go from D to C to A, then obviously, for example, when we go from C to A is a neighbor to C, but C is also a neighbor to A. So does that make an infinite loop or something? Yes, it does if we're not careful with the algorithm. And I'm just going to show you how this works in order to avoid that situation. That's exactly right. Okay, other questions before moving on to the code? Okay, so naturally recursive. What we're doing here is naturally recursive. The question about connection between D and E is fundamentally a question about the connection between D and C, C to A, C to B, B to E, A to E, and so on and so forth. Okay, so let's see. So we start with a graph object, as we have defined. That's one of the inputs. We don't really care that much about it. That's not going to change. And then we start from a node, which is we call it the source node. Okay, and then we want to check whether node 1 and node 2 are connected in the graph. Okay, and let's not, so for now just ignore that. Okay, so let me bring you back here. So following up on that question, let's start with D, and then we go to look at its neighbor C, okay? In order to see whether the node C is connected to E, I'm going to look at C's neighbors. So let's say that we start with D. Okay, that means that I go back to D, and then go from D to C, C to D, D to C. So that's an infinite loop. In order to avoid that situation, we are going to have to keep track of the nodes that we have already visited. Meaning that I have seen that node. I know that's not the destination node. I know there's not a connection there, right there. So I'm going to move on to the next. So I'm going to keep track of the nodes that I have visited. This is exactly what this visited variable here does. It says if visited is none, which by default it is, then we're going to say, we're going to store that node inside of visited. What is the data type of this visited? It's a set. Okay. Why is that important to save that as a set? Yes. It's for two reasons. So first is the time complexity, because storing that inside a set obviously doesn't incur any cost. The other reason is that a set avoids having duplications, because it's a hash table. The hash is the same, so there won't be any duplications. So we won't store a node over and over again when we when we look at it multiple times. Okay. If we use the list, then we probably have to add that node a couple of times to that list. So that makes our space complexity a lot larger. Okay, now I have a base case here. Let's ignore that just for now. But then this is the main loop. Okay, so we said that, okay, let's go through the neighbors of this current node. Okay, if V is already visited, if that particular neighbor is already visited, we're not going to do anything with that. We're going to skip this neighbor. And this is what continue does. What continue does means that don't check anything beyond that line in that for loop. So as soon as you see V in visited true, just go back up, ignore that neighbor, look at the other neighbors. This is the situation, this is the part of code that avoids that infinite loop here. So as soon as we get to C, we look at, let's say we start from D, and it says, okay, D is already visited. So let's go check out other neighbors. Okay. All right, so that's the first part. Then, if that's not the case, if V is not already visited, the first thing that we're going to do is to add that node to the visited set. Okay, makes sense. This is just for print statements. Don't need to care about that. And now here is the recursive call. Okay. Now what we're going to do is that we're going to take exactly the same steps with that particular node, with that particular neighbor of the source node. Okay. So here, the graph is the same. The target node is the same. However, I'm applying the same connected function, which is the function that I have defined, the name of the function here, connected. Okay, I'm going to apply the same thing over on that neighbor. So I have reduced the question of whether, for example here, whether D is connected to E to whether C is connected to E. So we're one step down the ladder there. Okay. And then we're going to recursively run this part. And then this is going to go look at C and its neighbors. And then it's going to check out one of the neighbors, and then one of the neighbors of that neighbor, so on and so forth. So it goes all the way until the end of graph if that element does not exist, if that node does not exist. And then it either returns true and false, and then just like other recursive functions, we go up we pop items from the call stack until we reach the base case. Okay, so this is a bit abstract like that. Now let's go through the same algorithm using a visualization. So, yes. Oh yeah, so that's exactly the purpose of this particular algorithm. So if that node is like disconnected, is like a separate island, then once we have done this algorithm, there is a set containing the visited nodes, right? If that element is not in that set, it means that there's a disconnect. Okay, now let me see. Yeah, I have it over here. Okay, here it is. So in the course repo, I have a link here for you. It's this one? No, this one. Oh, that's weird. Okay, it seems that I don't have that link there. Okay, I'm gonna add that. Okay, no problem. Let's do that. There's a very interesting website that I highly recommend for you to check out, and it's called Visual Go, so visual algorithms, and it basically has visualizations, step-by-step visualizations of algorithms applied on different types of data structures. It's super helpful to visualize what's happening in different kinds of algorithms. So you can see that already. We have sorting algorithms, binary search tree, and also all the way here we have graph traversal. Okay, so let's just choose a graph here. Example graphs, let me see. Okay, so there are two edges because by default this visual algorithm website only has directed edges between the nodes. So here we make sure that this is a bidirectional graph, meaning that you can take it to be similar to as a non-directional graph basically. Okay, so it means that directions don't matter. We have an outgoing node for each neighbor and also an inbound node from each neighbor. Okay, let's get started. I'm gonna open this pane over here to see what's going on. Right. What is the matter? some reason the whole thing is got stuck. So let me try a different browser. Okay. Firefox. All right. Accept. Okay, can any one of you try this website to see if it doesn't work for you as well? So let me just show that on the screen. So it's visualgo.net, okay. I don't know why the click button doesn't work. The play button doesn't work. Super weird. It doesn't work? That's weird. So it's broken right this morning? Okay, so let's see. So the graph is... the clicking doesn't work at all. Wait. So you mean this part? Okay. Yeah. Let's... Oh, okay, silly me. Yeah. All right. Yeah, I messed up. Okay. Oh, good. I have the graph over here. Okay. Yeah. So just ignore that thing that you saw, that depth first thing. Okay. So we start from node 0. The objective is to see whether this graph is completely connected or not. And you can here assume the worst case scenario where the node that we're looking for does not actually exist in the graph, so we have to search through everything. Let's get started. So node 0, okay, I'm going to go step by step. So here, we're going to check out node 1, and the way that we go through the neighbors is by their value in ascending order. So we're going to check out neighbor 1 and then neighbor 4. Okay, so neighbor 1, try edge 0, 1 here. So vertex 1, this node 1 is unvisited, so we're going to add that to the visited set. All right, that's added. Now, take a look at the code here. We executed this part, okay. Node 1 was not the one that we were looking for, okay. We skipped that one, and then we started searching through the neighbors. So we picked that neighbor, that particular neighbor 1, okay. This is the first loop over here. And then we say that if v in visited, continue. So v1 was not visited, so we're gonna go on to the next. We're gonna add that node 1 to the visited set. Okay, ignore this thing. And then now we are here. Now we are gonna do this. Instead of calling this function with 0, we're now gonna call this function with node 1, and then look for a node that is not inside of that graph. Okay, and we're using a node that's not inside of the graph because we want to search through the whole graph. Okay, so now I'm going to call this particular function, which is a recursive call. So I'm going to do exactly the same stuff, except for the fact that instead of starting from 0, I'm going to start from 1. Okay, let's see how that unrolls. So it says DFS1, meaning that apply this algorithm now on node 1. Okay, I'm going to check out this neighbor 0 because that's the smallest neighbor, number-wise. Okay, that is already visited, right? It says vertex 0 is explored. Okay, I'm now going to check out this neighbor 2 because 0, 2, and then 5. So neighbor 2 is not visited, right? So we're going to recursively call that function on node 2. Okay. All right, now we're at node 2. We're going to check out its neighbor. So we're going to check out neighbor 1 first. And then that is already visited. So what is the next node that we're going to go to? 3, exactly. So let's see if it does that. Yes, it's going to check out 3. Is 3 visited already? No. Okay, now we are now 3 levels deep into the recursive call. Okay, now we're at 3. Which node are we going to check out first? 2. 2 is visited. Okay, I'm going to check out 7 because that's the only other neighbor here. Okay, 7 is going to go back to 3. Okay, that's the neighbor. Go back to 3. That's already explored. Go back to 12. Okay, a recursive call is started here at 12. Okay, 12 checks 7. 7 is already explored. 12 checks 11. Okay, 11 is not explored. Again, call the recursive function. 11. These are the neighbors, so 6, 10, 12. We go to 6 because that's the smallest one. Okay. Check out 6. What is the first neighbor we're going to check out? That's 2. Yep. And then check 2 is already explored. We're going to check out 5. That's unexplored. Again, recursively call the function on 5. 5 is going to check out 1. 1 is already explored. 5 is going to check out 6. 6 is already explored. 5 is going to check out 10. That's not explored. Call that recursively. So I'm not going to mention all the steps here. Okay, go to 9. 9 checks out 8 because that's the smaller number here. And then 8 is going to check out 4 because that's the smaller number here. Okay, and then 4 is going to check out 0. 0 is already explored. Okay. Now that 0 is already explored, we can return from this particular recursive call here, that particular neighbor. Okay. Now that 0 is already explored, we're going to check out 8. Okay. Now, both neighbors of 4 are now fully explored. Okay. What's going to happen next? It says finish DFS4, this function, recursive function here, and backtrack to 8, meaning that we are now at the bottom of the call of the recursive call, and now you can return. Okay, now we return from 4. 4 is done, completely done. We're now going to return the result to 8. Okay. Remember that each one of these nodes is still waiting for this function to return something, and for this one to return something, for this one to return something. So remember, some of the nodes still have unexplored neighbors, and this is what we're going to do when we go back. Okay, we're going to go back to 8, and with 8, we didn't check out 9, right? Okay, so it says try edge 8 to 9. Okay, now we're going to check that out. As soon as we do that, we have checked out everything about 8. It means that we can return from that. So this is, again, completely done. Now, with 9, we didn't check out 10. Same thing goes here. Okay, 9 is done. With 10, we directly went to 9, so it means that 11 is now checked out. Okay, 10 is done. With 5, we checked out 1. We checked out 6. We came this way, right? 6 to 5. Okay, 5 checked out this one. 5 checked out this one. And then, okay. And now it says finish 5 because there wasn't any unfinished business at node 5. Okay, with 6, when we got to 6, we checked out 2, and then we checked out 5. So we can go to 11 now because that was waiting there. Okay, 11. All right, now it says 11 is already explored. So everything about 6 is explored. We're going to go backtrack to 11. Okay. And then 11 was waiting, so it only checked out 6 there, right? Because that was the smallest one. But this is already visited. We're going to go back to 12. That wasn't visited. That was one of the neighbors that we were waiting for. Okay, that is done. Vertex 12 is explored. Now we can return from that, and I'm going to go back all the way here. All right, in the same way. Okay, now this was so remember that when we started from 0, we went directly to 1. We didn't check out this neighbor over here. This is why at the end of the recursion, we are checking out the second neighbor of 0. This is why we're checking out 4. And as soon as we do that, we are done with everything. So you can see that we have checked out every node in the graph using this algorithm. Let me just restart it, run it all the way from the top. Maybe with a, okay, so a main feature of this algorithm is something that is very similar to binary trees or search trees. What is that feature? When we make the recursive call, something is happening. That's a particular property of this kind of algorithms. Do you remember that for... Yes, exactly. So when we started from the root node with the binary search tree, we had to go all the way down along one branch, and then when we returned from that, we checked out the other node, and then the other node, and then we started going down the other branch. It's the same thing happening here, and this is why this particular implementation of a graph search is called a depth-first search. Okay, depth-first search. This is why this is called DFS here, depth-first search. So it goes and looks in depth first, and then comes back up and checks out other neighbors of all the nodes. Okay, yes. Yeah, great question. Let me see if I'm gonna discuss this somewhere here. I don't think I will. Okay, so so what do you think? What is the time complexity of this algorithm? Let's ask another question. What is can you think of a lower bound, the minimum number of steps that you have to take in order to run this algorithm? The minimum. The minimum, right? Twice? Yeah. So just conceptually, in order to run this algorithm, we have to visit every node at least once. Right? So that's just like looking through an unsorted list. You have to look through things at least once. So that's a lower bound. But let's find what's the time complexity. So right now, if we denote the number of vertices is V, we know that this is at least O of 1. Oh, sorry, O of V. Okay, number of vertices. Okay, but is that the entire story? Okay, so imagine the case, so for a complete graph, yes, a complete graph is the worst case scenario where each node is connected to every other node. So it can't be just this, right? It also depends on what? Yes, the number of edges, not the total number of, total degree, sorry. So it also depends on the number of edges. Okay. This is the time complexity of the depth-first search algorithm. And the reason that we also have this edge here is that when we go and check out each node, we're also going to check out each neighbor. And the reason that we're going to check out each neighbor is because we have an edge to that neighbor, right? Okay. When we go and check out each neighbor, that neighbor is also going to check out the parent node, right? So in fact, this is more like 2e. But we ignore the constant factor, and then we are left with O of number of vertices and also the number of edges. Yes? Yes, exactly. So it's not exactly n squared, but if this was a complete graph, yeah. Yeah, it would be, sorry, not n, it would be v times v minus 1 over 2. And this is O of v squared. And in that case, this algorithm would be O of v squared. Okay. Any questions? Okay. So let's take a break of 5 minutes, and then in the meantime, maybe you could think more about this and come up with more questions. So we're going to be back in 5 minutes. Okay, we're back. So let's just show you a couple of examples for you to believe me that this algorithm works here. So draw this graph. We're going to want to find out whether A is connected to B. That should return true. Well, I forgot to run this. Okay, so draw the graph. All right, A connected to B, that should be true. Well, disconnected. Oh, I forgot to run disconnected maybe. Somewhere here. No? Sorry about the scrolling. Disconnected. It was, okay. Right there. All right, let's come back. This part. Draw this, and hopefully, no. It's direct cause of node 1 is not in the graph. Let's run this. Nope. Okay. I'm going to get confused if you all... yeah. Oh, yeah. I changed something here. Oh, my God, yeah. Right. Yeah, okay. Well, yeah, A is connected to B, and A is not connected to E, so this returns false. And there's a bunch of other assert statements here, which all pass for different kinds of connections between the nodes. Okay, and we just gone through the order of going through the nodes, so I'm not going to cover this example here, but I have returns print statements for you to check out the order of things being traversed, the order of nodes being traversed. So you can check out this example as well, but I think a much better option would be to check out this visual algorithm website. Okay, right. So can you tell me one particular downside with this algorithm? So suppose that you're making not a general query, but a special type of query. What would be a downside of this? Yes. If you have two islands, but okay, but you still have to search through the one and then the other and then the other. So it doesn't really matter if you do that recursively or any other way, right? You still have to check everything, basically, right? In each island, we have to check everything. Sure, yeah. To each other, 2 and 3? Yeah, that's right. So we have to go and run that algorithm on those islands too. That's correct. Yeah, that's correct. But there's like a more interesting downside to it, yes. Exactly. Excellent, exactly. So the example that we saw here actually showed this very nicely. So suppose that we're looking to see if 0 is connected to 4. Oh, okay, this is not a really good way to do that because 4 is right besides 0, right? We have to go all the way down. So it might be nice that for particular kinds of for particular kinds of queries that you want to make, it would be nice to have an alternative algorithm that doesn't have this particular shortcoming. Okay, so it's depth first. It goes all the way and then goes back up and then goes all the way and back up. And it's going to not see that neighbor that was right besides it if it has a larger index, basically. All right, so now let's check out a different type of algorithm, which is called a breadth first algorithm. So instead of going deep, it first checks out all the neighbors in each layer and then goes layer by layer. Okay, and in that situation, because we're going to check out all the neighbors in this layer, if that element is right there, we're going to see that immediately or after just a few calls, after just a few iterations, and then that will be much more efficient. But before that, I'm just going to quickly talk about these two data structures that we have talked about just about a little bit in previous lectures. Let me see if we have time. Okay, 1154, yeah, that's okay. So, two classical data structures that are very useful. Before that, let me get that question. Yes? Yeah. Yeah. So if that's equal to, so it won't help with the time complexity because you still have to visit every node. You still have to visit every node. But it might be an alternative way to write the algorithm. That's my guess, but I have to think more on that. Yeah. Okay, so stacks and queues. Previously in lecture 3, we discussed the call stack, if you remember. So stack was a particular data structure that you put items in it, and then the first item that you can return from it is the item that you inserted last, because it's a stack. You're going to put things on top of each other, and then the first item that you can pick up is the last one that you put there. So that was like a call stack. You build up the call stack, and then you pop the last recursive call, pop the other one, until you come back to the original caller. Okay, so that's just the definition of a stack. And here I have this stack data structure. It's super simple. You have the data inside of a list, and then when we append something to it, we just append to the list. When we pop something, we pop from the list, which by default pops the last item. So it's exactly what we wanted. Okay, and isEmpty is just a method to check whether length is equal to 0. So if this is so simple, why are we defining it using a class? Why doing all that stuff over here? Because whenever we use this object inside of our code, as soon as somebody sees it, that person says, oh, okay, this person is using a stack. But if I use just append and pop and len equals 0 and stuff like that, it's not immediately obvious that this is a stack implementation. So this is why. We just abstract things away. We put the details, just sweep them under the rug, and then we just use the abstraction here. Okay, that's a stack. Another kind of, these are just a few examples. Stack, we push these items onto the stack first, and then second, when we pop, the element that's going to be popped and removed is going to be the second one. And remember that whenever we're popping something, we actually return that from that operation so that we can do something with it. We're not just removing it, we're also returning it. Okay, now push third and fourth, print S, it's now first, third, fourth, and then now we're going to pop fourth, and then again pop, so fourth, third, and then pop again, that would be first. And then if we do another pop, it says pop from empty list. Okay, so just a couple of simple examples. A queue is only different compared to a stack because a queue is just like any queue in the real world, any line. So the first person that gets in line is the first person that gets served, right? So here, when we push things onto a queue, then when we pop the first item, not the last one. Okay, so the first thing that got added to the queue will be the first thing that will be popped and served. Okay, so you can see the difference here. Queue, push these two items onto the queue, and then when we pop the first one. This operation is also called dequeuing. Okay, so this is something that we are going to need with our breadth first search algorithm. Okay, so what we have done previously with the depth first search was using a recursive call, and now we can actually implement the same kind of graph search iteratively. So let's see how this one works. I'm going to explain the code to you first. It's a little bit more tricky because of using the queue over here, but I'm going to explain that on the visualization that I'm going to show you. So let's just bear with me with the code, and then we'll just jump over to the visualization, and everything will hopefully be much clearer. So we have a queue which in which we keep track of the elements or nodes that we haven't visited yet. Okay, so the way that it works is like that. Okay, we have an empty queue. We start from the node, the source node. Okay, we say, okay, you just get in the line, first node. All right. So that's the first node that's going to be served. Okay, we say that pop that element from the queue. Okay, I'm going to serve you. Now we say that, are you equal to the thing that I'm looking for? If yes, then just return true. We're done. You're not, I'm going to look for your neighbors. So the first thing in the queue, I'm going to ask it, are you the thing that I'm looking for? That person says no. I'm going to ask, are your neighbors the thing that I'm looking for? So I'm going to add the neighbors to the queue. I say that, okay, I served you. You can go and be added to the visited set. Now I'm going to serve the neighbors. So the first neighbor, are you the thing that I'm looking for? That person says no, okay? And then that's get added to the visited. I'm then going to serve, I'm then going to add the nodes of that one. I'm then going to add the nodes of that one onto the queue, and then I'm going to talk to the next one. Okay, are you the thing that I'm looking for? It says no. Okay, and that node is served. And then the next one, and then the next one. So in this approach, you can already see that we're going to look at each and every node before going to the next layer. Okay, so the first thing that we're going to check out is all of the elements that have a distance of just one step away from the source node, and then 2 steps away from the source node, and then 3 steps away from the source node. Okay, now questions about the code before moving on to the visualization. Okay, let's move on. So, coming back here, I'm going to use, so you can see here, depth first search. I'm going to choose breadth first search, and we're going to start from 0, and I'm going to prevent this from running. All right, let's start from 0. So, start from 0, I'm going to check out the neighbors. So, the first thing, first of all, this node was added to the queue, and because the queue was just contained only one element, I'm going to serve that element. I'm going to ask the question, who are your neighbors? So 1 is the neighbor, okay? And this one that appears here means that that's the first layer, okay? So is 1 already visited? No. So I have to add that to the queue. Okay. Now I'm going to check out the other neighbor. Was 4 already visited? No. So it means that we don't know anything about its neighbors. So I'm going to add that to the queue. Okay. Now, when I click next, it says the queue is now 1 and 4. So now the queue only contains these 1 and 4 items over here. That's the first layer. You can see that we go we propagate layer by layer from the source node. Okay. So now we're going to pop elements from the queue here. So I call 1, hey, come here. Who are your neighbors? Okay. So this one is already visited. We're not going to put that in the queue. Okay. We're going to go to 2. Is that one visited yet? No. Go in the line. Okay. All right. So that's the first item in layer 2. Is 5 already checked out? No. So get in line. 2. Okay. And now this is the second layer just belonging to this item. So let's see. Now the queue contains 4 to 5. Okay. So now we're going to serve element 4. Okay. Note that when we checked out this node 1, we popped it, meaning that we have completely served it. We popped it, only its neighbors were added. Now there are only its neighbors in the queue, okay, 2 and 5. Now we're going to serve the last node in layer 1, okay. Who is your neighbor? It's 0. Okay, is that visited? Yes, so just ignore that. Okay, who is your other neighbor? 8. Is that already visited? No, get in line. Okay, so now the second layer is complete. Now if I click next, look at the queue, 2, 5, 8. Okay, we have completed layer 1, layer 2, and remember that if I was looking for 4, I would have found it in layer 1. So breadth first, okay? Now, okay, I'm gonna serve the first element here. I'm gonna pop that, okay, pop that. Who are your neighbors? 1, we don't care about that. 3, get in line. 6, get in line. Now we are done with neighbor 2. Now these items are in the queue, 5, 8, 3, and 6. Okay, now we're gonna serve 5, so remove it from the queue. We're gonna serve you. Who is your neighbor? 1, don't care about that. Who is your other neighbor? 6, okay. And 10, yes, you can get in line. All right, that's the first item, the second item in the, sorry, the third item in the third layer. Okay, now, what is the other item in the queue waiting? That's 8. Okay, 8 here. Who is your neighbor? The first one is 4, already served. The next one, 9, get in line. Okay. Now the queue are these, contains these items, 3, 6, 9, and 10, and 9. Okay, so that's the third layer. One more layer, 2 more layers to go. Okay, we're gonna serve element 3. Look at its neighbor, 2 is already served. 7, get in line. Okay, now we have covered all of the neighbors of 3. I'm gonna move on to the next item. Okay, 6. Okay, that's the next one in queue. Pop that, look at its neighbors. 2, already served. 5, already served. 11, not served, get in line. Okay. Now, we're gonna move to 3. Okay, let's look at its neighbors. 5, already served. 9, okay, is explored as well. 11 is also explored and visited. Okay, so that's done. And then 9, again, everything about 9, all of its neighbors are already explored. So we're not gonna add anything new to the queue. Okay, that's done. That completes the 4th layer. So now we have everything in the 4th layer. Last items, check out 3, already served. 12, not served, get in the line. Okay, 11, everything about 11 is already served. Okay, that's the 5th layer. Now, we start, the last item on the queue is 12. Check out its neighbors. 7, already served. 11, already served. Where at the bottom, the breadth first algorithm is complete. Okay. So the main idea, the main takeaway is that I'm gonna look at the neighbors of all the nodes first, and then go on to the second layer, or go on to the neighbors of the neighbors. Yes? If you do that, so you pop the last element. That's right, yeah. Yeah, that's right, yeah. Okay, one implication of this algorithm is that the moment that you see a node for the first time, that actually, the number of steps that you have taken to reach that element is going to be the shortest distance to that element. Because that's the first time you have seen it and you're going layer by layer, that's got to be the closest, the shortest distance to that element. So that's one property of that. If you are interested in finding the shortest distance between 0 and let's say 6, you have to do it using the breadth first algorithm. Okay, otherwise you can do it with the depth first, but you're gonna incur a lot more computations and then keep track of things, which is not worth it. A more sophisticated algorithm that can be implemented using this BFS algorithm is the shortest path problem, in which on the edges you also have distances between the points. So here the distances are taken to be 1, but in that case it's going to be more complicated. But again, most of the graph algorithms, a lot of the useful graph algorithms are implemented using these 2 particular approaches, breadth first and depth first algorithms. And this is why we have covered it. I have talked about these 2 algorithms in this lecture in full detail. Okay, so let me run this code and just show you a couple of examples. So the graph that I'm looking at is this one. Let me see if I have a visualization of that. Yeah, it's here. Okay, so 0 to 14, we want to check whether 0 is connected to 14, and it is connected to 14. So 0 through this node 3 is connected to 14. Okay, and then this is when we try verbose. It just prints the level. Prints all of the nodes that it visits, and you can check whether this algorithm that we have written corresponds to the visual one that I've just shown you, and it does. Okay, so you can just follow the nodes that are visited, and you can see exactly what is the progression towards the item that we want to find. Okay. Now, one last point about this is that in this code, if I change this queue thing to stack, this will become the depth first algorithm right there. That's really beautiful, I think. And the reason this is the case is because in the previous implementation, we actually had an implicit stack, and that was the call stack. So this is why if you just change the queue, instead of getting people in line and serving the first one who got in, you use a stack, so last in, first out, then this will become a depth first algorithm. Okay. And again, in the previous case, we had an implicit stack, and that was the call stack. All right. So let me see, we have covered, everything that I wanted to cover. All right, so we have a few minutes left. Maybe we can check out a couple of activity questions. Okay. Activities. All right. Student groups. Okay. All right. So true and false. Maybe. Okay, let's take a minute or two to think about these statements, and then I'm going to ask you whether you think the statements are true or false. Okay, just maybe 2 minutes. Okay, let's, all right. So if you think that statement is true, just raise your hand. If you think it's false, just don't raise your hand. So statement 1, to model Twitter relationships, one would naturally use a directed weighted graph. True or false? For true, raise your hand. Okay. I'm going to ask you, so one of the people who raised their hands, why do you think that's the case? We have to use a directed graph, but weighted. Why do we need a weight? Okay, all right. But between a person A and person B, do we need a weight? Because it's either I follow you or I don't follow you. So in that case, yeah, okay. Sure. Yeah, that's a great point. And yeah, exactly. It's not like that this is always true or something like that. So I just wanted to make this discussion going. That's a great point. You can assign a weight if you want to actually, for example, model the amount of interaction between those two people. But in the simplest case, if it's just based on follow or unfollow, then in that case we don't need a weight. It's just a directed connection. Okay. So again, if you think a statement is either true or false, and I give you an answer, that doesn't mean that this answer is always true, always has to be the case. Maybe you have another idea that makes a lot of sense in this case. Okay, in an undirected graph, there is a path from A to B. If there is a path from A to B, then there is a path from B to A. Is that always the case? No, it doesn't have to be. Okay, that's why it's directed, so that we can have connections from A to B, but not from B to A. Okay, number of edges in a graph must be less than or equal to the number of nodes. So, true? It's false because, yeah, if you have a complete graph, you can have this many edges, which is obviously larger than, okay. So 4, the number of edges in a graph must be more than or equal to the number of nodes. False, right? You can have a graph that's just islands of nodes, right? Okay. So let's check out this other question. Just maybe think about it for 2-3 minutes, and then we'll look at the answer. So consider the task of finding a path through a maze like this. And then you want to represent this maze as a graph. Okay. And then you want to use a breadth-first search to find a path from the start to the end. When representing the maze as a graph, what would you use as your vertices, and what would you use as your edges? Just think about it and feel free to discuss if you want. All right. Any ideas? Yes.
Every branching point or every dead end has a node the path connected.
Yeah, that's exactly right. So for this one, we can represent each branching point or intersection, and also the dead ends as a node, because, for example, you start from here, you have to decide whether to go this way or that way, so that could be a node. And then this dead end could be just an ending node, and then the path between the two could be represented by an edge. So again, for example, we can have a node here and then a node here connected through this path. Again, here, no. Right here, for example, we can have a node that can go either this way or this way, and a node here for the dead end, and then a node here, because again, we can go this way or this way. So something like that could represent the maze, and using the, for example, the breadth first or the depth first algorithm, we can find our way out. Okay, so I think that's it for this lecture. Thank you, everybody, and good luck with your quiz today.